All right, let's dive into a classic, and I mean classic computer science puzzle. How do a bunch of independent computers share something safely when there's no central boss calling the shots? In this explainer, we're going to break down two really brilliant solutions to this exact problem. Lamport's groundbreaking algorithm, and then Ricard Agrawala's super clever optimization of it.
So yeah, this is the central question, right? Think about it. Imagine a shared file, or a record in a database. On your own computer, it's easy. The operating system is the traffic cop. But what happens in a distributed system? You've got a whole group of computers, or processes as we call them, and they all have to agree on who gets to use that resource next. And remember, no one's in charge. So how on earth do they pull that off?
Okay, to really get this, we need to get two key terms straight. First, you'll hear critical section a lot. That's just a fancy way of saying the piece of code that's actually touching the shared resource. And second, mutual exclusion. This is the big one. It's the absolute non-negotiable rule. Only one process can be in that critical section at a time. If you mess this up, you get total chaos and corrupted data. It's that serious.
Now, you might be thinking, okay, that sounds simple enough, but trust me, in a distributed world, this problem is incredibly tricky. Let's dig into exactly why it's so hard.
The challenges here are really fundamental. First off, there's no shared memory. One process can't just peek at a variable to see if another one has locked the resource. They're flying blind. Then, there's no global clock, so you can't just look at a timestamp and know for sure who asked first. And, like we said, no central boss to grant permission. So everything, and I mean everything, has to be figured out by sending messages. And these messages can get delayed, they can arrive out of order. It's a mess.
So with all those challenges, how do you even build a solution? Well, it turns out any correct algorithm, any solution that actually works, has to follow three golden rules. These are totally non-negotiable. You can think of them as the holy trinity of mutual exclusion. Rule number one, and this is the big one, safety. I mean, this is the whole reason we're doing this. At any single moment, at most one process is allowed in that critical section. If two ever get in at the same time, the algorithm has completely failed. Period. End of story.
Okay, next up is liveness. This is the rule that makes sure the system doesn't just grind to a halt. It means you can't have a situation where a bunch of processes are all stuck waiting for each other forever. You know, a classic deadlock. The system has to make progress. If someone wants access, someone, eventually, has to get it. And the third rule is fairness. This is all about preventing what we call starvation. That's where one poor process just keeps getting unlucky and is skipped over again and again and again. It never gets its turn. So the best way to be fair? Simple. Grant access in the order the requests were made. First come, first served.
All right, now that we've laid down the law with our three rules, let's bring out our first contender. This is the foundational algorithm from the one and only Leslie Lamport. It was one of the very first to just elegantly solve this whole mess.
So the big question is, how does it work? How do you get that first come, first served fairness when there's no global clock to tell you who was actually first? Well, this is where Lamport's genius comes in. He invented something called logical clocks. Basically, every request gets a timestamp. And if two timestamps are the same, you just use the process ID to break the tie. It's such a simple trick, but it creates a single, totally ordered line, a queue for the whole system. It literally creates order out of that chaos of network delays.
The protocol itself is kind of like a three-step dance. Step one, a process wants in, so it sends a time-stamped request message to everybody. Step two, it waits. It has to sit there and wait until it gets a reply, which is basically a permission slip from every single other process. Then, once it's done its thing, we have step three. It sends out a final release message, telling everyone, okay, I'm done, the resource is free again.
Now, here's where it gets really interesting, the cost. Let's say you have n processes in your system. For just one trip into the critical section, you're sending n-1 requests, getting n-1 replies, and then sending n-1 releases. Add that all up, and you get a total of 3 times n-1 messages. It definitely works, but wow, is it chatty. Keep that number in your head, 3 n-1.
And that chattiness brings us perfectly to our second algorithm, this one from Ricard and Agrawala. They looked at Lamport's incredible work and basically asked a really simple but powerful question. Can we do this with fewer messages?
And their big idea was just so clever. They realized that whole third step, the release message, was kind of redundant. They thought, what if we could bake that release logic right into the reply messages?
So instead of just blindly replying yes, the processes can make a smarter, more conditional decision.
This is the crucial part, this new reply rule. So, when a process gets a request, it thinks. It replies right away only if one of two things is true. Either it doesn't care about the resource right now, or its own request has a later timestamp, meaning the new guy gets to go first. But if it's currently in the critical section, or it has an earlier request, it just holds on to that reply. It defers it. And that deferred reply, sent out only after it's done, that becomes the signal for the next process in line to go. It's brilliant.
This single insight just completely streamlines the whole thing. The dance goes from 3 steps down to 2. All you do now is broadcast a request, and then you wait for all the replies. That third release step, poof, it's gone, totally absorbed into that new, smarter reply logic. And the result of this? Well, the message cost drops big time. You still have the N-1 requests and the N-1 replies, but that's it. Your total cost is now just 2 times N-1 messages. That's a huge improvement.
Okay, time for the head-to-head. Let's put these two titans of distributed computing right next to each other and see how they stack up.
So when you look at them side by side, it's clear they both rely on that same core idea of total ordering to make sure everything's fair. But the real difference, the game changer, is that message complexity. Lamport's algorithm needs 3 different types of messages, giving it that 3n-1 cost. Ricard Agrawala, on the other hand, cleverly gets it done with just 2 message types, bringing the cost down to 2n-1.
And believe me, that difference has a massive impact in the real world. Let's just take a small system, say 10 processes. To do the job, Lamport's algorithm needs 27 messages flying around. But Ricard Agrawala, it only needs 18. That's a full 1/3, a 33% reduction in network traffic. We're not talking about a minor tweak here. This is a serious, fundamental optimization.
So, okay, we've clearly established one algorithm is way more efficient. But you might be wondering, so what? Why should I care about a few extra messages? Well, let's talk about why this matters so much.
Because in any large-scale distributed system, messages are the lifeblood. They're everything. Fewer messages means less network ingestion, which means lower costs. It means the whole system performs faster because there's just less waiting around. And maybe most importantly, it means the system can actually scale. You can add more and more processes without the whole thing getting bogged down by its own chatter.
And that really leaves us with a final, important thought. You know, in today's world of massive, decentralized systems, we're talking everything from the cloud infrastructure that runs the internet to blockchains. These principles, pioneered by Lamport and then refined by Ricard Agrawala, are more relevant than they have ever been. It's a classic problem that reminds us to always ask, in a world that is built on communication, what is the true cost of sending just one extra message?